Okay, welcome to the grand tour of the CAN bootloader system, or as I like to call it, the part where everything finally starts to make sense. Let's set the scene. Imagine a modern car, dozens of little computers all gossiping with each other over the same two wires, all funneled into one single connector, the OBD port. Now imagine giving your devices that same superpower, but without paying a manufacturer £10,000 for the privilege. That's exactly what this CAN bootloader does. It lets you manage and program multiple STM32 devices through one single CAN port, no matter how busy the bus is, how the system is, or how much caffeine you've had this morning. Now, here's the clever bit. Each device builds its own unique CAN identifier using its factory-programmed 96-bit ID. That means every device ends up with a one-of-a-kind 29-bit extended CAN address. It's like giving each microcontroller its own passport, and nobody is arguing over whose device won. This also means we're deliberately staying out of the way of the standard 11-bit CAN identifiers. Less chance of collisions, less chaos, less time wondering why your LED controller is suddenly flashing your motor controller instead. It's funny once. After that, not so much. Compatibility-wise, I've already prepared bootloader binaries for two popular chips, the STM32F446 and the STM32F407. But if you're using a different STM32F4 variant, don't worry, I can build the correct version quicker than a compiler can crash because you forgot a semicolon. A quick word about licensing. The bootloader and the flashing software, CAN Flash Studio, are closed source, release binaries only. But the support libraries you use in your firmware, those are fully open source. You can browse them, modify them, or frame them on the wall if you're particularly proud. You will need a PeakCAN USB adapter. That's the bridge between your PC and the CAN bus. Without it, your computer just stares at the CAN wires like, ah yes, electricity. CAN Flash Studio works on Windows 10 and Windows 11. If you're on Mac OS, well, sorry, you can still watch though. Cheer us on from the sidelines. That's the warm-up done. You've got the overview, you know what the system does, and you know what tools we'll be using. Let's get CAN Flash Studio installed. First, download CAN Flash Studio using the link in the description. The download will arrive as a zip file. Once that's finished, open the zip and inside you'll find an installer named canflashstudio.msi. Run the MSI installer and treat it like any normal Windows install. The default options are absolutely fine, no need to overthink this part. I'm going to assume your PeakCAN hardware and drivers are already installed and working. If not, don't worry, there are plenty of good guides available. I'm skipping that here purely to keep this tutorial short and focused. Once the installation finishes, there's one important thing I want you to notice for later. By default, CAN Flash Studio installs to the root of your main drive. On most systems, that's the C drive. You'll see a folder named Automotive Electronics. Inside that is CAN Flash. That folder contains the main application files, but also notice a folder named STM32. Inside the STM32 folder are several helper and support files that we'll use later in the video. You don't need to do anything with them right now, just remember where they are. Future, you will be very happy you do. Alright, let's move on to the fun part, flashing the bootloader. I'm going to assume you already have the ST tools installed, such as Cube Programmer and Cube IDE. If not, go install them first, then come back. Go ahead and open Cube Programmer. This is the tool we'll use to flash our bootloader exactly once. Yes, this is the first and the last time we'll be using Cube Programmer for this entire project, so enjoy this special moment. Now connect to your device. I'm using an ST-Link, but USB DFU works too. Once you're connected, you'll see a big table on the left. It may look like a bingo card written by a robot, but don't worry, it's just a readout of your flash memory. We're not changing any of that manually. On the top left, look for the icon with three little horizontal lines stacked like a tiny hamburger menu. Yes, the same sneaky menu every smartphone app uses. Click it, then select Erasing and Programming. Before we continue, make sure these two options are checked. Verify programming and run after programming. These ensure everything flashes correctly and actually starts running when it's done. Now, this next bit isn't strictly required, but I like doing it anyway. Click Full Chip Erase. Cube Programmer will take a moment and then proudly announce something like erase successful. Good, clean slate achieved. Next, we need to tell Cube Programmer which bootloader binary you want to flash. Click Browse. Remember earlier when we located the binary files inside the folders, automotive electronics, then CAN flash, then STM32, then binary? Head there again. For my demonstration, I'll be using the file bl_STM32F46RCT6.bin. Select the correct file for your microcontroller and click Open. Take a deep breath and click Start Programming. Cube Programmer will flash the bootloader, verify it, and then give you a nice confirmation message. If it doesn't, well, that's a different tutorial entirely. At this point, you can disconnect your ST-Link or unplug USB if you were using DFU. Put the programmer back in its drawer. You won't need it again for this. Close Cube Programmer. From this moment on, everything we do will be handled through CAN Flash Studio the way it was meant to be. I want to say this right at the very beginning. I am genuinely excited to show you this next part. This is where everything finally comes to life, and we get to explore CAN Flash Studio, the tool that brings all of your hard work together into something real and interactive. Before we jump into the software itself, here's a quick recap of my setup for this demonstration. I already have my hardware powered on and ready to go. I'm working with 5 nodes connected on the CAN bus, along with a peak CAN interface, all neatly wired and properly terminated. At the moment, CAN Flash Studio supports classic CAN only, not CAN FD, and the bus speed is fixed at 500 kilobits per second. If you're still watching, still listening, and still following along, thank you. Your support genuinely means a lot. If you'd like to help this project grow, feel free to like, share, and subscribe. It costs nothing, yet helps more than you'd imagine. All right, with all that said, let's launch CAN Flash Studio and dive in. All right, go ahead and launch CAN Flash Studio from the desktop icon. Give it a moment while it wakes up, stretches its legs, and initializes the peak CAN device. During this time, it will attempt to connect to the CAN bus. If everything is behaving itself, you'll be greeted with the main screen of CAN Flash Studio. If something isn't behaving, don't worry. An error message will appear with a simple explanation of what went wrong. No cryptic codes or ancient riddles, just a clear message. Once the connection is established, the peak CAN interface sends out what's called a ping frame. This is a special CAN message with a fixed ID and some specific bytes. And remember that bootloader we talked about earlier? Whenever it hears this ping frame, it immediately replies with the device's unique ID. That's how CAN Flash Studio knows a device is alive on the bus. In my setup, I have 5 nodes. Nodes is just a fancy word for CAN devices running the bootloader. As you can see, CAN Flash Studio has detected all 5 of mine. If I open the drop-down list, I can see nodes 0 through 4, but they're all listed as unknown. Why? Because CAN Flash Studio only knows that they exist. It has no idea what you want to call them. So let's fix that. On the left side, click Device Editor. A window will appear telling you that you have a number of unknown nodes. Below the message, you'll see a drop-down containing the 5 unique IDs, each one representing a device on the CAN bus. We now need to map each of these IDs to a friendly human-readable name so both you and CAN Flash Studio know what they represent. But how do you know which ID belongs to which physical device? Here's the honest answer. You don't, not at first. The simple method is unplug one device, restart CAN Flash Studio, and see which ID disappears. Repeat until you know what's what. For this demonstration, I already know which device is which. So I'll select the first ID, click Add, and it moves from the list into the table. The table works very much like a tiny spreadsheet. Click into each cell to edit its details. Make sure you fill in the chip name, flash size, and RAM size so everything is identified correctly. Once you've mapped all your devices and filled in their details, look to the left and click Save All Changes. Confirm with OK and the editor will close. Now, if I open the drop-down again, you'll see that all the nodes are no longer called unknown. They're now properly named with the friendly labels I assigned earlier. And here's the good part. You only need to do this once. The bootloader stores its ID internally, so even after a power cycle, everything stays exactly as you named it. No need to repeat the process every time you switch the system on. Now that our devices are identified, organized, and behaving themselves, It's time to move on. Next, I'm going to show you how to create a blank project in Cube IDE that can be flashed using CanFlash Studio. Before we flash anything using CanFlash Studio, we need to cover the absolute minimum project structure required inside Cube IDE. Don't worry, I'll take this step by step, slow and steady, nice and clear. We'll start completely from scratch by creating a brand new project in Cube IDE. First, open Cube IDE. At the top, click File, then New, then STM32 Project. This opens the target selector screen. This is where we tell Cube IDE exactly which STM32 chip we are working with. Since I'm using an STM32F446, I type STM32F446RC6, select the device from the list, and click Next. Now give your project a sensible name. I'm calling mine CanTest STM32F46RCT6. Boring, yes, but very clear later on, which you'll appreciate. Set targeted language to C++ and make sure targeted project type is STM32 Cube. Click Finish. Cube IDE now opens the STM32 configuration tool. This is the graphical setup screen where we configure clocks, peripherals, and GPIO pins. For this demonstration, we'll only configure what we actually need. No extras, no distractions. On the left-hand side, click System Core, then click Sys. Under Debug, choose Serial Wire. Even if you're not actively using an ST-Link for flashing, having debugging available during development is always a good idea. Think of it as cheap insurance. Next, set the time-based source. I leave this as the default sysTick, which works perfectly for most projects. If your project needs a hardware timer, you can change this later. Still under System Core, click RCC. My board uses an external high-speed crystal, so under high-speed clock, I select Crystal Ceramic Resonator. My board does not have a low-speed crystal, so that option stays disabled. Now go back to the left panel and click Connectivity, then CAN 1. Enable CAN by ticking the activated checkbox. Next, open the NVIC Settings tab and enable all available CAN interrupts. The library we use handles most configuration automatically, but the interrupts must be enabled manually. Cube IDE won't do that part for you. By default, Cube IDE assumes the CAN pins are on PA12 and PA11. However, I deliberately move them to PB9 and PB8. Why? Because if your project uses USB, those USB pins cannot be reassigned. USB permanently owns PA12 and PA11, so moving CAN avoids future pain. Future you will thank present you for this. In the pin diagram, click PB9 and PB8 and assign the correct CAN functions. If your hardware uses CAN 2, repeat this process there. Mine does not, so I'll leave CAN 2 disabled. Now head to the top and click the Clock Configuration tab. Because we told Cube IDE that an external high-speed crystal exists, this is where we configure the PLL timing. In the input frequency field, enter your crystal value. In my case, that's 8, since I'm using an 8 MHz crystal. Now find HCLK. This sets the system clock speed. I want the system to run at 84 MHz, so I type 84 and press Enter. Cube IDE will ask if it's allowed to use other clock sources to achieve this frequency. Click OK and let it do the maths for you. It's much better at that than humans. Once the clock configuration finishes, go to the top, click File, then Save. Cube IDE will now generate your base project and you're ready to move on to the next step. Now, we're going to import the required library files. Remember earlier when I said CanFlash Studio installs additional support files? Good news, it really did. We just need to tell Cube IDE where they live. We're going to import two important files, ini.c and ini.h. These files do a lot of the heavy lifting behind the scenes, so don't skip this part. Future debugging pain starts here if you do. First, look to the Project Explorer on the left and expand your project. You'll see a folder named Core. Expand it, and inside you'll find two folders, SARC and INC. Now open your System File Explorer. Navigate to the CanFlash Studio installation directory. This is typically C drive, automotive electronics, CanFlash, STM32, project library. Inside that folder, you'll see the two files we need, ini.c and ini.h. Drag ini.c into the core SARC folder in Cube IDE. If Cube IDE asks whether you want to copy the file, click OK. Next, drag ini.h into the core INC folder. Again, if Cube IDE asks to copy the file, click OK. And that's it. We need to modify the linker file. The linker script runs every time the project is built. Among other important jobs, it tells Cube IDE where your firmware should live in flash memory. Quick but important note, this file is chip specific. The layout depends on how much flash and SRAM your particular STM32 has. In my case, I'm using the STM32 F446RCT6. That gives me 256 kilobytes of flash and 128 kilobytes of SRAM. Now, remember the bootloader we flashed earlier? That bootloader occupies the first 32 kilobytes of flash. So if we don't tell the linker about this, your application will try to live in the same space, and that never ends well. We're going to fix this manually. Don't worry, it's simpler than it sounds. In the Project Explorer, scroll toward the bottom and find a file named STM32F446RTX-flash.ld. Make sure you open the flash linker file, not the RAM one. This is important. One wrong click here equals instant confusion. Double-click the file to open it. The good news is we only need to modify a very small section. Scroll down until you see the memory definition section. This section defines where flash and RAM start and how large they are. Here's what we need to do. We change the start address and length so that the application is placed after the bootloader instead of on top of it. In simple terms, we're telling the linker, skip the first 32K. That's bootloader territory. Next, we need to align stack to exactly 16 bytes. This is important because CANFlash Studio checks this alignment, and if it's wrong, it will complain. Loudly, just follow along and set it exactly as shown. One final step. We need to add a meta label so CANFlash Studio can verify that this firmware was built for the correct chip. Under the ISR vector section, add the required chip identification label. This tells CANFlash Studio very clearly which STM32 this firmware belongs to. And that's it. To finish up, go to File, click Save, and then close the linker file. Your project is now correctly placed in memory, bootloader safe, and ready for flashing. Alright, before we move on to adding the minimal application code, there's one last thing we need to sort out, and it's an important one. By default, Cube IDE generates something called an ELF file. That's spelled ELF, and no, unfortunately, it doesn't come with a tiny hat and pointy shoes. However, CANFlash Studio does not speak ELF. It only understands bin files, spelled BIN. So we need to tell Cube IDE to generate a bin file automatically every time we build the project. Here's how to do that. At the very top of Cube IDE, click Project, then select Properties. On the left panel, expand C++ Build, then click Settings. Now look for the category called MCU-CUs, MPU Post-Build Outputs. Inside that section, you'll see an option labelled Convert to Binary. Tick that checkbox. Once that's done, click Apply and Close at the bottom. And that's it. Cube IDE will now generate a proper bin file every time you build your project, ready for flashing through CANFlash Studio. Now we're finally at the point where we can write the minimal code needed for your project to work with CANFlash Studio. And I really do mean minimal. Every project you want to flash over CAN will need these same pieces. Let's walk through it. Inside main.c, look for the section labelled User Code Begin Includes. In that space, add the include for the INI library. This gives your project access to the functions that handle all the CAN bootloader communication behind the scenes. Right below that, you'll also add the meta tag. This tiny line tells CANFlash Studio exactly which chip the firmware was built for when it generates the bin file. Without it, the software will look at your bin file and go, no idea what this belongs to. Scroll down to the section labelled User Code Begin 0. Here you'll add two small library objects. These create the internal structures the library needs later, essentially giving the bootloader somewhere to store its CAN state and configuration. Next, keep scrolling down into the actual main function. Just below the area marked User Code Begin 2, add the CAN initialization code. This sets up the CAN interface so the library can talk to CANFlash Studio. If your hardware also uses CAN2, the process is exactly the same. I'll show the line for CAN2 as well, but since I'm not using it on this board, I'll comment it out. Finally, move into the while one loop, the main loop of the firmware. Just below, user code begin 3, add the polar function. This is the part of the code that continuously listens for incoming CAN traffic and responds to CANFlash Studio. The great thing is that it's non-blocking, meaning it won't slow down or interrupt any of your own logic running inside the loop. Once all that is in place, go to the Project Explorer on the left, right-click your project name and select Build. If everything was typed correctly, you should be greeted with the most beautiful sight in all of embedded development: 0 errors. If so, congratulations, your firmware is now ready to be flashed over CAN. Alright, now that we've enabled bin file generation earlier, remember that little checkbox we ticked? It's time to actually find the bin file Cube IDE created for us. Here's where to look. On the left side of Cube IDE, right-click your project name. Hover over Show In and choose System Explorer. This will open the folder where your entire project lives on your computer. Think of it as Cube IDE saying, here you go, this is where I've been hiding everything. Open the main project folder, then open the debug folder. Inside, you'll see a bunch of files, some you recognize, some that look like they belong in a museum. But the one we care about is the .bin file. It will usually be named after your project. For example, mine is CANTEST STM32F44C6.bin. Let's make life easy when we switch to CAN Flash Studio by copying this file to the desktop. Just right-click the bin file, choose Copy, go to your desktop, right-click and paste. Nice and simple, and now the bin file is exactly where you can find it without playing hide and seek with Cube IDE. Alright, so first of all, yes, I do apologise that this part took a little longer than expected, but trust me, I just wanted to make sure everything is explained properly, clearly, and in a way that absolutely anyone can follow. Start by opening CAN Flash Studio. We already covered the startup process and how to configure your nodes, so I won't drag you through that again. Relax, your brain gets a break this time. You should see your nodes detected. In my case, it has already selected node 0, accelerometer. On the left-hand menu, you'll see an option called Select Device. Go ahead and click that. This screen is wonderfully simple, but also surprisingly powerful. Now again on the left menu, click Open Firmware Binary. Browse to the bin file that we copied to the desktop earlier and hit Open. A little window will pop up. Don't panic, it's just scanning and verifying the bin file to make sure it looks correct. If something isn't right, trust me, it will shout about it immediately. Mine seems good, so you'll notice the menu item Flash Firmware is now activated. And this is the moment where you cross your fingers, toes, arms, legs, whatever you've got, and click Flash Firmware. You'll see the progress right on screen. Once it finishes, the device will automatically start running whatever you just flashed, and you'll get a lovely confirmation message telling you the update was successful. If you want to triple check, just power cycle everything and reconnect. You'll see all the configuration settings exactly as they were. And that's it. I promise it does not take this long when you're doing it normally without me narrating every atom of the process. Now, I want to show you a real practical example of using the library to send and receive CAN messages inside your own project. This is where things start to feel real and a little bit fun. Open Cube IDE and load the project we just created. Once the project is open, locate the library objects we previously added. Now we're going to add a new function. This function creates a user callback that receives all CAN traffic seen on the bus. Every message, nothing hidden, nothing fancy. Inside this function, we first check which CAN peripheral the message belongs to. Two simple lines determine whether the frame came from CAN 1 or CAN 2. Next, we create an if block for CAN 1. This means the code inside will only run when a message is received on CAN 1. Inside that block, we add a simple switch statement. For this example, the logic is very straightforward. If a CAN frame is received with an ID of hex 10 and byte 0 equals 1, then we send a response message. Once the code is added, I build the project and flash the new bin file using CAN Flash Studio, exactly the same way as before. I'm not going to walk through that process again, you've already conquered that boss level. Now for the fun part. Open PeakCAN View and connect to the CAN bus. Create a new CAN message with ID set to hex 10 and byte 0 set to 1. This is the exact frame we just programmed the firmware to respond to. Send the message onto the bus. And boom. You'll immediately see the response appear above it. The message with ID hex 200 and the 8 data bytes we defined. Congratulations! You just sent a CAN message, received it in firmware, processed it, and replied. All using the library. Hopefully this gives you a clear insight into how you can use this setup in your own projects. And yes, once you understand this, the rest is just variations on a theme. Now let's talk about activating your license for CAN Flash Studio. CanFlash Studio is available as a free download, and in the free version you get 20 flashes. We think 20 flashes is more than enough for you to decide whether this tool is something you want to keep using. After that, we kindly ask for a small fee to unlock full, unlimited lifetime access. The activation key isn't expensive, and every purchase helps support future development, new features, improvements, and keeping the whole ecosystem healthy. So let me walk you through how the activation process works. On the main CanFlash Studio window, look at the menu on the left and click License and Activation. A window will open asking you to enter an activation key. Now you might be thinking, but I don't have a key yet? No problem. Just below, click the Request button. This opens a small form with fields for name, email, transaction ID, and additional notes. And if you're wondering, but I don't have a transaction ID either, that simply means you haven't purchased the program yet. On the right-hand side, click Purchase. This will take you to the PayPal checkout page where you can purchase your activation key. After payment, PayPal will send you a receipt. That receipt contains your transaction ID. Now fill in the form with your details, including the transaction ID, and click Generate. This creates a pre-written email and stores it on your clipboard, ready to send. Open your preferred email application, create a new message, right-click in the body, and paste. At the top of the message, you'll see the address it needs to be sent to. Just send it off. After that, please allow 1 to 48 hours for me to personally create and send your activation key. Once you receive it, enter it into CanFlash Studio, and just like that, full access is unlocked. One important note, the activation key is machine-specific, meaning it is tied to your computer. The same key will not work on a different machine, and that's the whole activation process. Simple, quick, and designed to keep everything running smoothly. Before we finish, I just want to say a huge thank you for sticking with me this far, and honestly, bonus points if you haven't fallen asleep yet. That alone deserves applause. My goal with this video was to properly explain CanFlash Studio. No rushing, no magic, no just trust me moments. Some of you will find it genuinely useful. Some of you might think, yeah, not for me. And that's totally fine. Either way, I really appreciate you taking the time to watch, learn, and give it a chance. That support means more than you probably realise. If you need to get in touch, you can email me, at lukehoward20287@gmail.com. Yes, read exactly like that. No guessing, no panic typing. And finally, a quick thank you to Vecteezy for providing some of the royalty-free clips used in this video. Thanks again for watching, take care, and I'll see you in the next one.